Okay, now this is 3.4, the remainder and factor theorems. In fact, there's another, the most important theorem. It's in the very end. So I would divide 3.4 into two recordings. Now, first one, we will talk about the remainder and the factor theorem. And then the second one, we'll talk about the rational root theorem. And in fact, this remainder and the factor theorems, that both are the preparation for the third theorem. And third theorem, and all three together, it is basically trying to help us to find the roots. All right, so now let's take a look at what does the remainder theorem means. So now, first of all, in last section, we already know that fx, if that is divided by, this is the dividend, if that is divided by this divisor, and then this is would be the quotient, and then this is the remainder. All right, so now you must have noticed this remainder. So sure, this is either could be 0 or it's just a constant value. So this is only divided by a this degree of 1, the polynomial, by this binomial, but the degree is 1. So divided by this, then the remainder will be just a value, either 0 or some other different numbers. But in the example that I demonstrated last section, if fx is divided by a trinomial, so divided by ax squared plus bx plus c, and then you have a quotient, and then your remainder here is not a value, but your remainder is a 1 degree lower, which is could be a mx plus b. So I just wanted to point this out. Some of you might have already realized this. I just find these things very interesting mathematically. All right, but however, we do not really consider this kind of thing. The reason why is we're trying to find the root of the polynomial function. So we're trying to find the root of the fx. So then that means if we have this one as the divisor, and then of course we have a quotient, and if our r equals to 0, then that means we have this left, and then that means there's a roots such as x that equals to 0, when this fx, when fx equals to 0. Then you have this one equals to 0, then x equals to a. Bingo. So this a is one of your zeros, one of your roots. So basically the remainder theorem says that we just need to take a look at this, what's going on with the remainder. As far as the remainder is 0, then we know that this a is our root. So another way is to say if fx is divided by x subtract a, and the remainder is 0, then that means a is our root. So also, so the theorem now says is that how can I make sure this is 0? So that says that if you divide it by x subtract a, and the fa is your remainder. The fa is your remainder. So how can we think this way? This way here says is because if you say f equals to a, so x equals to a, And then that means FA equals to A minus A, so then that becomes 0, so this thing is gone. So then FA equals to your remainder. So this is what we're trying to say here. All right, so here it says if the polynomial Px, or you could say Fx, is divided by x subtract a, then the remainder is the PA. So now take a look at here. So you don't have to use a long division to calculate the remainder. You don't have to use, you could use a long division. So for example here, you definitely can use just the 2x to the power of 4 minus this plus 2x subtract 3. You use this to divide it by x2. So in the end, you will have a remainder of 3. But using the theorem, we can just put this 2 into the x. Calculate that, and that's your remainder. So that is basically what the theorem is talking about. Okay. They use the synthetic division. They have some kind of merit of using this because it's just easy to calculate rather than plug the number in. However, the reason why we say, first of all, we don't even have time this year. Second, the synthetic division, it only works for when you divide it by a degree of 1. It won't work for divided by a degree of 2, let alone higher. So, but the long division works for dividing by anything as far as it's lower than the degree of the dividend. So that's why we say we don't do this. Any of you would like to see how that works, you can go ahead and self-study. Okay, so then here we say the k is divided by, well, not the k, the whole px is divided by that. Now how much is the k? How much is the k means how much is the remainder. So then again, we plug this 2 into each x and calculate that, and the k equals to that. Okay. Then this one says to find the remainder. And then again, find the remainder, you just have to bring this -1 into each of this x, and then you find the remainder again and again and again. So right away, we should just get into now factor theorem. So the factor theorem is a different way. It's absolutely a different way to say whether or not something is the zeros, or something is a 0, or something is a root. So what does it mean? If it's px is divided by that, and there's no remainder, then that means this a is the root. So now, for example, so say whether or not this is a factor. So whether or not it's a factor means whether or not it is a root. The same thing. As we look at it, the different way to say about the a, x minus a, it could be a factor, or that means a is a 0, or a is a root. So all the different ways to say that. So the question is whether or not this is a factor also means whether or not the -2 is a root, whether or not the -2 is a root. So now here we go. Then we bring this -2 into the x and calculate it, and then in the very end, it is a 0. All right. Now again and again, you can use the long division. This is divided by x plus 2, and to see whether or not the remainder is 0. Now the next question is to say whether or not this is a factor, or whether or not 1 is a root. And then here we go, the remainder is -9. So I'll plug this 1 in, the remainder is -9. Then therefore, this is not a factor, and therefore 1 is not a root of this polynomial. Okay, now factor theorem. So now it says let P be a polynomial function, so Px. The polynomial Px has a factor of that if and only if the remainder is 0. Yeah, sure, right? Means if and only if. So what does this mean? So trying to figure, further explain if and only if means that implies two separate parts to the factor theorem. So that means if the remainder is 0, then that is a factor. Or if this is a factor, therefore that is absolutely a 0. PA is a 0. So if and only if means you can reverse the order of what you say. You can say this one first, and then you can say this second. If you say this one and that one, and both has to be true. And of course, obviously, both are true. Okay, so now does okay, one again and again is a little bit too repetitive now here. So then bring this 2 into the polynomial function, and yes, remainder is 0, and that's yes, x minus 2 is a factor.